You've seen LLMs using chain of thought to think out loud, but that's still generating text, token by token. What if an AI could have a private mental drafting board? A hidden workspace where it could form a complete, coherent plan before it outputs the first token. This is a core idea behind reasoning in latent space. Today, I'll be breaking down 3 cutting-edge approaches to show you the mechanics behind this potential next generation of AI. So first off, I'm going to do a quick LLM refresher so that we're on the same page as to how these things work. And then I'll talk about latent space reasoning, what's involved, and 3 different techniques. So while the transformer was originally devised by Google in 2017 with the encoder-decoder model, OpenAI ran with just the decoder-only version for their generative pre-trained transformer models, the GPT models, which form the basis of GPT-1, 2, 3, ChatGPT, GPT-4, etc. So these models are trained to predict the next token. As we can see on the right-hand side for inference mode, if I put in the cat sat on the, I hope that the output for the word the would be the word mat, or it's basically there's a distribution over words in which mat may be one of the highest selected choices. So you can see that as we go through the transformer, closer to the bottom we've got stuff which is quite close to the original word, but as we go up, because we're mixing in a whole context and we're also altering the contents of that individual representation, we're morphing what's in at the bottom to the next word at the top. Now, one of the reasons these are extremely effective is when we're training them, we can put in the original sentence, but we also know the result at every position just by shifting the sentence over by one. By carefully controlling what each of the tokens is allowed to look at, i.e. it can only look backwards, we can make sure that we can train all of these things simultaneously rather than one token at a time. So this parallelism is one of the key benefits of these transformer models, and also for this autoaggressive setup in particular. You can see here possibly that the colors on the tokens are slightly different on the outputs than the inputs, because at the top we're getting an approximation for which token we're going to get out, but we then choose from this distribution at inference time. But at training time, we have essentially a cross-entropy loss, which is trying to get this as close as possible to what the next token should be. Interestingly, during the pre-training, we only train essentially for the truth, rather than letting the model devour its own outputs. So the models, after they've been pre-trained, only know what it feels like to respond to true inputs. They've never consumed their own outputs at that stage. In post-training is the first time we actually get them to see what happens and how to recover from their own mistakes. And this points to one of the issues which held us back with smaller models with less data, in that if a small model trained on little data got into trouble with tokens it produced, it would never be able to rescue itself. Whereas these huge models, because they have so much experience of what people recovering from errors looks like, they are able to recover themselves. So this is kind of an interesting phase change where suddenly the pre-training in this essentially professor mode, where you tell it, okay, here's your input, here's your output, is sufficient to make it generate long contexts, even as a base model. So let's drill down a bit on this token in and token out idea. So we have tokens coming here as the input, and a model like Gemma 2 has a vocabulary size of tokens of like 262,000 potential tokens, which is a very large vocabulary, particularly compared to like a GPT-1 or 2. But if we think of what this 262K is it's actually 2 to the 18. Basically, this is an address within a table which has 2 to the 18 entries. That is to say, all that a token represents is 18 bits of information. We know that for a fact. On the other hand, if we look at Gemma 2 9b hidden dimension, which is 3584D, this is way, way bigger, and in fact unimaginably bigger than 2 to the 18. So each of these dimensions is more than plus or minus 1, which would represent the 2 in 2 to the 18. Ideally, we'd have a full 32-bit floating point number, but of course we could quantize it these days. On the other hand, when something is 3000 dimensional, it's way, way bigger than 18. In the same sense that something which is 3D is not just like one extra dimension bigger than a 2D sheet of paper. You can think of the 3D as being like an infinitely larger space than a 2D piece of paper. So 3000 is not just a little bit more than 18, 3000 is colossally more than 18 in terms of dimensionality. Now in the last layer, this is going to convert the 3000 odd dimensions back into, via a softmax or some other distribution selection, this 2 to the 18 number, which will be coming through to being the next token. On the other hand, surely, one might say, surely there's rich information inside this hidden dimension which we're not being able to pass on to the next layer. In particular, for these transformers, they've learnt that the last layer, or just before the last layer, they do have very rich information which has been passed up through all of the tokens and attention to come to very rich information before producing the output. But they've never been trained so that that rich information is being input. All we're getting is 18 bits of information at every step. We're throwing that away. Because of the way they're trained, the input has never been able to see that rich information coming up. So that brings us to the latent space. We know that these models, even though we train them only on token-wise steps, do have an impression of like the state of an argument, a sense of the topic, over much longer timescales than single tokens. What if we could unpack this knowledge better, instead of just converting it down to single tokens, which is the only task we've trained them for? We could actually use this rich information to continue to inform the stream from the tokens upwards, rather than just the last layer. So I'm going to talk about 3 different approaches to this latent space reasoning: recurrent depth, latent tokens, and large concept models. And these are in no particular order, and this was just taken from like a point in time back in April or so. So the idea of recurrent depth has actually existed for quite a long time. Back in 2019, we had universal transformers and Albert. So one of the threads in universal transformers is how we can actually do more computation on a token, essentially by rolling out more thinking time for each token, or depending on how complicated the token is. I have to say this didn't seem to catch on, but one of the driving ideas is, with a fixed number of steps, the transformer doesn't appear to be Turing complete. It can't consider every token like it should. Therefore, we should be able to have a variable number of tokens available. As another example of doing repeated computation, we have Albert, which basically replaced the multi-layer BERT structure with a single transformer layer which got repeated a large number of times. Now, the goal of this paper, or at least the reported goal of this paper, was to save parameters. You only need to save the parameters of one layer, and then you're going to repeat it again. So one of the things which wasn't emphasized, though, is whether this saved you flops. In particular, it doesn't save you any flops because you're still using that layer multiple times. You're still doing the same number of matrix multiplies. Nowadays, you might imagine that it could save on bandwidth since you have these things loaded locally, but that's a discussion for another day. So for this recent recurrent depth paper, we're going to split the transformation into several steps and do a variable number of them. So on the top, we have the word hello being put into some kind of precursor network to make it into a rich latent space. And then we're going to pass in noise modified by this essentially guiding signal through multiple layers of these recurrent blocks. And these recurrent blocks are the same thing again and again. And then at the end, we're going to take the result from that latent space and pass it through kind of an exit block, whereby it's going to get converted back into a word, which should be a next word prediction thing. So this is, in a way, a more modern take on which layers to repeat, informed by investigations that people have done into what is occurring at the end stages of a transformer, in the depths, in the middle of a transformer layers, and like right at the beginning few layers. So the interesting thing with this is you can now also plot out how much the test time compute, like how often you repeat these layers, affects your final accuracy. And you can see here with these beautiful curves, as you apply more test time compute, you're getting better answers. It's not actually saying that we can determine when we should stop. On the other hand, it's clear that test time compute is a benefit here. So reading between the lines on this paper, it seems that the authors did 3 major runs at training them. And it seems like there were bold fixes between the runs to try and get it to converge. So they have a code repo, Apache 2, and they have open weights, super nice research, and it kind of demonstrates that this approach works. On the other hand, they do point out, don't get too excited because it doesn't beat Olmo 2. So basically, it's not as if this method is achieving super great results, but it's kind of a proof of concept stage and still difficult to manage. So the next method is called Coconut, where there's code released and there's a nice blog post to read. I've left a link to the paper in the description. Instead of decoding just the last hidden state into a token, the idea is just to try and feed the state itself as input into the decoder, which seems like a logical thing to do. So this representation is used as the embedding for the next step, instead of just reading the embedding from a table, and we just progress with the autoregressive process as normal. So here's a quick picture of what these latent tokens look like. On the left-hand side, we can see the individual tokens as numbers being passed from top to bottom. And then on the right-hand side, we can see this latent representation being passed in, and then the latent gradually gets more and more involved as time progresses. But the problem is we don't know how to train the model to respond well to the latent being passed in, because that presumably is much more complicated than what it's reading out of the embedding table. So the trick to training here is to gradually replace tokens with these latent representations. So you start with a pure chain of thought in tokens and gradually take out a token and replace its embedding with the latent from the previous step. We then gradually train the model to do this with more and more of the steps of reasoning being replaced with these latent tokens. Hopefully this thing will now cope with being passed in a more complex object at the beginning. Now, it's not clear here that we're actually going to save tokens in doing this, since all we're doing is we're training it to respond to tokens being put in with the same output as before. But the hope is that by being passed in a richer environment, it will learn to take advantage of that and essentially reduce the length itself. So the results, I would say, gave so-so accuracy. They do claim that there's fewer tokens being used. But the paper also identifies that there's a lot more scope for exploring these ideas. Not only could you look for different tokens, you could play with what latents you're going to use. You would use this for kind of planning. This is fertile ground for experimentation. In fact, there's later work which claims better results. I'll leave a link to this in the description. I'd be happy to cover that in a later episode. If you'd like that, please leave a comment. The third method I'll talk about is called large concept models. Facebook has published a very extensive paper where they combine different kinds of representations and exchange in and out different mechanisms to find out what works and what doesn't. It's very encouraging that they would publish this kind of research. One of the key aspects here is it makes use of a previous Facebook model called Sonar. Now, Sonar is a system of encoders and decoders, which has been trained on 200 languages and also multiple modalities. Basically, Sonar creates embeddings which it can either go from text to an embedding or from an embedding to text. So this is like an autodecoder mechanism, but has been extensively trained and tuned by Facebook. So here's the Sonar repo, which has been around for quite some years. You can see, as I said, that there's basically for multiple modalities, including speech, they're coming to a single embedding. So Facebook is using these embeddings as being the latent space to train a model on, so that the model doesn't go between tokens, it goes between these embeddings. Essentially, we're training a model at a higher level, and then we can read it out by asking Sonar to express the current latent space as, say, a sentence or a phrase. So here's a diagram from their paper where they show on the very left side essentially a chain of reasoning through latent space, and then on the right side of the diagram here is just the endpoints of this chain of reasoning. So this is in some sense a transformation between the argument and the logic of it. Now on the right hand side we can see that the words are going to be transformed using Sonar into these concepts. Passing them through this large concept model, we get out different concepts which can be translated into words. Now, this is a very brief summary of a 49-page paper. They used several different kinds of models, both regular transformer decoder models and also diffusion-based models. They were also interested in whether they could quantize the concept vectors. They were also interested in what kind of targets to use. With a token-based approach, we actually know concretely what integer we want out of our network. But if we have a large representation coming out of our network, is it that we want to match it piece by piece within the hidden dimension, or is there some other way that they both have to classify to the same point in space? Basically, we've got a lot more flexibility about how these things should be matched. All of these variations were explored in the paper, and the results were not entirely clear-cut in that some things worked in some situations, other things worked with a different mix. Basically, this is laying out a roadmap for the kinds of experiments which will follow, and hopefully we'll hear about those. One key issue underlying all of this is whether these Sonar embeddings are really good for chaining thoughts together. So while Sonar can convert text to a representation and back to text, it is not clear whether moving from text to the next thought is actually going to be a useful way for a transformer to learn how to do this. It's not clear, it's not a good idea, but it's also not proven that the Sonar embeddings are good, that they have definitely not been trained such that they would be good for this. So here we're essentially using an autoencoder trained for in-place re-representation, and then hoping that these representations are logically connected to each other in a path that could be learned by a network. On the other hand, this is a very interesting use of a pre-trained asset, and it will be very interesting to see what happens next. So to wrap up, I think it's a bit too soon to declare that latent space reasoning is a thing, or this is the right horse to back. On the other hand, this is definitely something to watch out for, and possibly open for even the GPU poor to experiment with. On the other hand, I should point out that it requires extra engineering, and maybe this is in opposition to what the bitter lesson tells us. So here's a single frame from a lecture given by an OpenAI researcher. This illustration shows how he thinks of compute and how it relates to performance of a system. When doing research, it's very tempting to put a lot of structure on top of how your system is learning in order to push it in a direction which seems good intuitively. And so this would be the blue line here, where adding structure gives you early wins. But one of the lessons that he takes away from OpenAI's experience is that as you remove structure and just make the system learn from data, it will become more capable of picking up the ideas itself. Furthermore, if you go for an even less structured approach, learning from even more data and applying even more compute, in the early stages it may underperform the original systems, but later on, when it has got the idea of what it's meant to do, this is when the bitter lesson starts to apply, in that being able to scale purely by adding compute, rather than humans fiddling with the knobs, this is the way to achieve excellent performance, in a way which becomes increasingly realistic as the cost to compute declines. Another thing to wonder is whether we're victims of history to a certain extent, which goes back to the hardware lottery, which is Sarah Hooker's paper, which talks about how the early winners in hardware. So this could be network architecture. In our case, typically doing matrix multiplies or attention matrices, leads to the hardware becoming specialized for those methods. We can see this, for example, with Google's TPUs and the increasing focus on inference chips, which have very reduced functionality because you know the sole target of your architecture is going to be a limited number of operations. Suppose instead that this latent space reasoning was made easier by having a very recurrent learning, or maybe a very sparse learning, or a spiking firing. Basically, those routes to performance have been ruled out because of our current choice of hardware, and it's going to be difficult to prove that they would be effective because we're now locked into a particular hardware setup. Anyway, these are just two caveats to the broader question of whether this is an interesting area for research. It remains to be seen. So thank you for watching this episode. I'd be glad to read comments if you leave them below. In particular, I'd be glad to do episodes about things suggested in the comments, whether it's programming or research papers or new models. The goal of this channel is to really look at research proactively, since it shouldn't just be left in the hands of the large proprietary labs. There's still a lot that can be done, even by the GPU pool. And with that, cheers.